So with all these concepts in our mind, we worked hard to make Molecule. Don't worry, guys, we are not going to talk about chemical formulas. I'm not Walter White. Molecule is an architecture based on Redux concept made by three main parts that we like to call atoms. We have a composable state, the store, and the observable view model. I'm going to introduce you them, and I also going to introduce some other parts of this architecture that in our opinion are essential too.
Hi guys, we are Enzo Corsiero and Pasquale Spisto, both iOS engineers at Telepass. Today, we are going to talk about how we found a solution to the problem that every one of us, sooner or later, has to resolve, which is the legacy code inside our applications. We'll look at 4 different sections. What was our problem and how we found a solution, a description of our solution, where we are going to talk about our architecture, a sample to use. We made a Pokédex using the public Pokemon API and our architecture. And the next step that we have in mind to further improve our architecture. We initially used Katana, an open source framework inspired by Redux for handling business logic, and Tempura for managing navigation, both developed by Bendixponse. The centralized state allowed us to have a single source of truth for each specific moment. However, we have found the same limits using Katana and Tempura. For example, they didn't fully support SwiftUI, the architecture was inflexible, and it wasn't possible to divide our app into submodules. Furthermore, we found that teaching new employees to use Katana was time-consuming, which became a problem when we had to expand our team. Katana was also highly dependent on HydraSync, which had some limitations such as lack of priority management. In addition, HydraSync is based on promises and semaphores that suspend the entire thread of just the single task. Last but not least, it's important to note that Katana is no longer maintained, which could lead to problems in the future. To summarize, the main reasons that prompts users to choose the right button and experiment with the new technologies were the lack of modularization support, the HydraSync dependency, the architecture rigidity, the lack of full SwiftUI support, and that Katana was no longer maintained. To address the challenges we were facing, we divide our team into 3 squads, each with a specific focus. The first squad worked on creating a new architecture. The second one focused on integrating the composable architecture into our app. And the third squad explored using vanilla SwiftUI to see if it could meet our needs. By splitting the team into these 3 groups, we were able to explore different solutions simultaneously and find the best path forward for our project. So, the first squad was tasked with finding a new architecture that allows for modularization, be compatible with SwiftUI, and maintain compatibility with Katana and Tempura. This was important because we didn't have enough time to build the app from scratch. and the code base wasn't old. Maintaining a large code base is a challenge that all teams face. The second squad focused on studying the TCA, but encountered several problems when trying to integrate it into our app. We have to say that this brainstorming started almost 2 years ago, when the TCA was still in the alpha version. Some of the limitations we found included a lack of support for Swift concurrency, the verbosity of the architecture when used with Katana, the difficulty of using 2 different architectures in the same app, and the difficulty of doing onboarding using 2 different architectures. Ultimately, considering the upsides and the need to expand our team, we decided to give up on this route focused on TCA integration. It was possible, but too expensive. The last squad focused on using vanilla SwiftUI and came to the conclusion that our project was too big for an architecture vanilla SwiftUI based. This was because it represented a significant change in paradigm compared to the Katana architecture, which is a prime example of centralized state compared with a decentralized state used in vanilla SwiftUI. This approach also would not add any benefits during onboarding sessions. None of the squad involved had found a straight solution, but by working together, they came up with the first idea for a new app architecture. Over the following months, the solution was improved until it became the best approach to take. During the creation of the architecture, we tried to maintain as much compatibility with the previous one as possible. For example, we kept the same Katana concept. As a result, it was integrated into the main app, and we are quite satisfied with the outcome. The new architecture coexists perfectly with the previous one. This is all about our approach to resolving the problem. Well, I would kill everyone in this room for a drop of sweet beer. Don't worry, guy, it's just a quote. I leave the floor to Pasquale, who will show you how Molecule is made.
Thank you, Enzo. Well, at that point of the history, we clearly knew what was our nice to have, but we also knew what were our must have. First of all, we should to make something that was fully compatible with Katana and as much as possible similar to it in order to speed up our learning process of what we were using. As a second point, we were younger than today, and we would like to have fun with new technologies such as SwiftUI and Swift concurrency. And the last point was to take our huge code base and make it as much as possible modular in order to easily maintain it. So, with all this concept in our mind, we worked hard to make Molecule. Don't worry, guys, we are not going to talk about chemical formulas. I'm not Walter White. Molecule is an architecture based on Redux concept, made by 3 main parts that we like to call atoms. We have a composable state, the store, and the observable view model. I'm going to introduce you them, and I also going to introduce some other parts of this architecture that in our opinion are essential too. Let's start from the composable state. As Enzo said before, the state is the source of truth of our application. And keeping in mind this concept and trying to achieve the modularity wish that we have, we tried to design something that could be seen as a composition of states of all the modules that we can have inside our app. So the result is the composable state, a protocol that we implement as a struct, which contain the dictionary of all the pieces of the state that we call substates. The substate is the element that contains the information of the module, and it also contains another particular element that is the identifier used by the composable state to retrieve the value from the dictionary. I would like to focus on the scope of each substate. With our solution, the dictionary of the composable state is always in memory, but not all the substates are accessible. Any of them will be accessible by the module that have visibility on a specific substate. In this way, the visibility of a substate is defined at compile time, and the scope of the entire composable state is restricted for a module. Anyway, Enzo will show us an example of that during the demo. Great. All this code is exciting. I can see your shining eyes. But at that moment, we had two main questions in our mind. The first one is, how can we manipulate the information inside the composable state? And the second one is, how can we store more other information in it? Well, to answer them, let me introduce you other two more concepts that are the side effect and the state updater. Well, a side effect is an isolated element that is not accessible from outside, but it can interact with the external world thanks to the context. Keep in mind this word, the context. We will see it in the next slide, where the side effect has a perform method in which you can describe your business logic, and thanks to the context, it is able to dispatch new action, for example, new side effects and new state updater. The state updater, instead, is the element that allows us to update the information inside the composable state, in particular inside the substate. It is always executed in a synchronous context, and as you can see, the protocol receives only, in the update state method, receive only an in-out parameter. That means that the state updater is not able to dispatch new action or new state updater. Well, let's move from the composable state to another atoms, that is the store. The store is the element of our architecture that contain the state and the environment. For us, the environment, it's only a container of all the dependencies that we have inside our app. For example, the network manager or any other modules manager. This object, the store, is not only a container, but is the object that is in charge to dispatch the action that we saw before. Thanks to three different methods that are the dispatch a side effect, a simple side effect. In this way, we can dispatch the side effect and wait for any result. Or we can use also dispatch and forget. That means that we can dispatch the side effect without wait any outputs. Please pay attention to the context, that is the word that we said before. The context is the abstraction that the store makes for a side effect of the external world. It allows to have a reference of the state and the environment to the side effect. So it allows to the side effect to use these two elements without keep any reference of it. And also the context allows to the side effect to dispatch new action like side effects and state updater. The third method that the store has is the dispatch of a simple state updater. That means that through this method we can update the substate. Well, all the pieces that we saw until now of Molecule are talking about business logic, data, so how can we store and manipulate it. We haven't talked about yet UI and Swift. Okay, thank you. I know what you are thinking. I got it? Yeah, okay. But don't worry, guys, the lunch is coming, but before, let's try to analyze what happens in our applications. Well, a person takes a smartphone and trigger an event. Maybe an event can also occur without a person. That means our app is going to manipulate information. So our app is trigger a side effect or more side effects. And the side effect will store information inside the composable state through the state updater. But as last part of this process, the app will update the UI. So we can say that the central part of this process, the two steps at the center, are led by side effects and state updaters. Instead, the last part is led by this object that is the observable view model. This object is our solution to decouple and abstract the UI from the store and the business logic. Any view model that inherits from the observable view model contains the store, which means that the view model can dispatch action in general through the store. It also able to receive update from the state thanks to the subscribe methods. The view model will notify the changes to the view thanks to the object will change publisher, and the view can keep the information updated through some computed properties that we will see during the demo. Well, the last piece that I like to show you is the view that we implemented that uses SwiftUI, and it has the possibility to subscribe itself on the state updates with two different approaches that are simple to understand what they mean. The first one is when visible, so the view will receive and will update information when it is visible, and the second one is always. Well, let's try to recap what we did and what we achieved thanks to Molecule. First of all, we get the modularity that we would. This thanks to the composable state and the abstraction that the store makes of the elements. As a second point, we introduced Swift concurrency that improves the performance over the Grand Central Dispatch. And as third point, we were able to introduce SwiftUI inside our app. And the last point, maybe the most important, is the interoperability with Katana. As anyone in this room, we were scared to rewrite from scratch the whole legacy code that we have. So thanks to Molecule and the interoperability between Katana and Molecule, we were able to rewrite just one module per time and not the whole app. Okay, let me leave the stage again to Enzo that will show you with a funny demo the framework in action.
Thank you, Walter. Okay, guys, now we are going to see how to use Molecule and how the UI updates. We'll take a look at some code blocks from a demo application developed using Molecule and SwiftUI. Who has never played Pokemon? We'll explore a Pokédex using the public Pokemon APIs. In this application, we'll be able to see the list of Pokemon, view their details, mark them as captured, and eventually release them. Before exploring the demo, it's important to provide a brief introduction to this app. To test its flexibility and to try this part as best as possible, we strongly use the notion of a modular app, dividing it into 7 submodules. But we'll now examine the state management of only 3 of these modules: Pokemon List, Pokemon Detail, and Code Pokemon. Let's focus on substate of these 3 modules, each of which has a substate defined within itself, except for Code Pokemon, which use a substate defined in another external module. These 3 code snippets allow us to make the substate visible to modules defined outside of the states module. However, to achieve this, it's necessary to import the substate object. We can also define a private substate object to restrict external access, if that is what we want. In this video, we can see how the list is updated when the last element becomes visible. Of course, we only see one example of a UI update cycle, and the best one is when the Pokemon list is updated. This happens both when the app is started and when the user scrolls to the last element of the list. We have just seen the starting point event. Now, let's take a closer look at what happens in this scenario. When the user scrolls up to the last element, the load Pokemon collection side effect is triggered. First, the current list of Pokemon is retrieved, which is necessary to call the API with the correct offset value. Then, another side effect is called to make the API call to load the new Pokemon. In this example, we can see how Pokemon are retrieved using the Pokédex client, which is a dependency within the environment that allows us to update Pokemon through network request. We won't go into detail the Pokédex client because it's outside the scope of this talk. This is the continuation of the side effect you saw 2 slides ago. It takes the result of the previous side effect, which is the new Pokemon list, and concatenates it with the old one. Finally, the update Pokemon collection state, which is a state updater, is called. As we saw earlier, state updater protocols are used to update the app state. Let's see how a state updater is used. A state updater simply assigns a new value to a specific piece of state. In this case, the Pokemon list substate is updated. Business logic must not be performed inside the state updater. It's simply a value assignment. But how does the view update after a state updater? We are examining how the Pokémon list view model is constructed. The view model contains a computer property called the Pokémon collection and two functions that invoke side effects. One to load the new Pokémon and another one to open the Pokémon's detail page. Let's focus on Pokémon collection. This property retrieves the Pokémon list via keypath, which points directly to the state. Therefore, whenever the view updates due to a state change, Pokémon collection always reflects the updated state value. Now, we have seen how the observable view model works. And it's important to notice that the current view model extends the observable view model. This approach ensures that the view is updated whenever the view model is updated by defining the view model with the state object property wrapper. Consequently, the body view is loaded every time that the state is updated. This is simply SwiftUI, guys. Now, let's look at how to test the code using the Molecule architecture. To test our application with Molecule, we have implemented the test store, which contains app state and environment, like the store. But the dispatch function gets a closure parameters in addition to the side effect. This closure allows us to set the expected final state value. In the example provided, we use the selected Pokémon and open detail side effect. And now we are going to examine what happens inside it. In this side effect, we are updating the selected Pokémon that we are navigating into the Pokémon detail view. You can notice the navigate functions in this snippet. Molecule allows to manage navigation, but it's still in alpha version and it isn't ready to present. We are still working to improve it. We can go back to the previous snippet. Here, we can look what we expected inside the state of the tester. We accept that the selected Pokémon is the same as one passed inside the side effect, and that after the side effect execution, the current selected route is Pokémon detail. That's all, guys. But since I don't see you very hungry yet, now I'm leaving the stage for Pasquale, who will tell you what else we have in mind to improve Molecule. Let's go.
I will be fast. Well, our roadmap is designed to improve Molecule. As you have seen during the demo, we already have something that allow us to navigate our application, but this part is based on the previous API of iOS, so that means that we want to improve it with the iOS 16 APIs. Another two steps are improves the dependency management, also in order to improve the testability of the components of Molecule, for example, a side effect. And as last point, we want to make Molecule an open source framework, because we think that it's a pleasure to share with you just a solution to our problem that maybe can be the same problem that you are facing or that you faced in the past. So I hope that this presentation is is something that could inspire you for the future solution of your project. Thank you, guys.